Yes, Matthew, let's go.
Perfect, thank you. So I'm Matthew Ballance. I'm here to talk about my project PyVSC, SystemVerilog-Style constraints and coverage in Python and beyond. So just by way of an introduction, a little bit about me. My day job, I work at AMD. I do verification methodology development and deployment, a bunch of SystemVerilog stuff, some portable stimulus, some other fun stuff. Spent about 20 years before that in EDA, developing, designing, and deploying various design and verification tools. Nights and weekends, I'm a pretty active hobbyist in design verification and tool development. There's a lot of fun stuff out there, and I certainly take advantage of getting to play with it. Kind of the areas I'm interested in are finding new ways to approach various design and verification tasks, and the tools that support those tasks. Kind of some focus areas. I've always been interested in sort of hardware-software code verification, and some of the tools that enable that, make that friendlier. Adding more instrumentation to designs to make system-level debug a little easier, and what will lead to this talk a little bit more, bringing Python into verification environments, either as an alternative to SystemVerilog or a complementary technology. On the open source side, due to the state of the tools, it tends to be a little bit more of an alternative. In commercial flows, it tends to be a little bit more complementary. Both are good approaches. Just by show of hands here, anybody use Python CocoaDB for verification? Oh, good, excellent. Got a good group then. Okay. So when I first started looking at Python as a verification technology, I was looking around the ecosystem, the landscape. There's some pretty good technologies for connecting Python to simulators. There's CocoaDB. There were some libraries that came along a little bit later, like PyUVM for adding some structure to your test bench, making things a little more familiar for people coming from more of a SystemVerilog background. There are libraries for doing various protocol interface, verification IP type stuff, and just in general with Python, there's a wealth of libraries for pretty much whatever you can imagine. The thing I didn't find coming from a SystemVerilog background was constraints and coverage. If you're from a SystemVerilog background, this is pretty fundamental. You look for how do you set up your constraints and do random stimulus generation, and how do you collect coverage from that. There were a couple of special purpose libraries, packet generation type randomization. There is a package that does some randomization, I think CocoaDB coverage, I believe. It's pure Python. It does a lot for what it does, for what it is, but it's pretty limited in terms of the complexity of the constraints it can handle. So for my purposes, looking for something that really looked pretty much like SystemVerilog and scaled to the complexity of constraint problems that I was used to dealing with in SystemVerilog, there wasn't an existing library that really fit those needs. And so I sort of decided to start playing with what could be developed in this space to fit those requirements. Okay, so first off, why do we care about constraint, random, and coverage? The designs we work with, whether they're for academic use, whether they're for hobby use or commercial, they get pretty complicated. Humans are pretty good at identifying at a test plan level, what areas do we want to focus on? What needs to be tested? Figuring out the details and elaborating all of those various test cases by hand, we're not so good at that. Well, first off, it gets dull, and it's actually a lot of work. That's where constraint random comes in. So constraint random allows us to specify constraints on what's legal, what makes a good test, something that we care about, and let automation, in the form of the constraint solver, figure out the specifics of what that test is. It helps us cover the space that we care about with some guidance. but it also helps to uncover key cases that we didn't think of. So really helps to find bugs very effectively. If you're from a software background, you might think of this as fuzzing. I'd say the biggest difference between fuzzing and constrained random for verification is for verification, constrained random is a primary testing methodology, whereas fuzzing is almost more of a backstop from a software background. Now, of course, when we're doing random generation, we need to know what we've generated. And that's really the first reason we need functional coverage. If you throw a bunch of random stimulus, you need to at least make sure that you've covered the key cases you care about. But functional coverage also really helps out to figure out what your design did internally. What key conditions that you were hoping it would get to, did it get to? What's missing? What new test cases? What new focus areas do you need to point the constraints to? All right, so what is PyVSC? Well, it's an acronym. It's not very imaginative, but it's basically a verification, stimulus, and coverage. So it's a library that encompasses both of those aspects, and it is in Python. Probably goes without saying, it's open source. It's up on pip. You can download it, install it very easily. So basically, it models both constraints and coverage. The goal is to keep the look and feel as close to SystemVerilog as possible. That actually is a primary goal of the library. And we'll do a little comparison later on to see how good that is. You can argue whether that should have been a goal, but given what people are familiar with, what they can often find resources on in terms of describing coverage, what code snippets exist out there, I thought that was a good design goal to maximize reuse. Now on the back end, so that's kind of the front end of the library, the user interface, so to speak. On the back end, it's making use of some very powerful constraint solvers. SMT solvers have made kind of a big leap forward in terms of the complexity that they can handle in terms of constraints, their speed, their capacity over the past 5 to 10 years or so. And this is really built on top of a lot of those advances. If you've used Boolector, Z3, any of these solvers, you've seen probably, you may have observed over time how much better they've gotten over time. So this is really standing on a lot of very deep technology that I didn't write myself, but I'm able to take advantage of because of open source, and it really helps out the project significantly. Okay, so the other aspect of PyVSC is that it has well-defined paths to get coverage data out to other flows. And that was one thing that I was also found pretty missing with the existing Python libraries. There wasn't really a great way to get the data out to other flows. And we'll talk a little bit about how PyVSC does that. All right, one question I do get oftentimes is, does PyVSC work with fill in the blank? CocoaDB, PyUVM, and the answer is absolutely. It's Python, there's really very little dependencies. You can use it with CocoaDB, you can plug it into your arbitrary Python script. It's quite friendly that way. Okay, so let's talk about the kind of the modeling aspect of PyVSC a little bit. Constraints are what we call a domain-specific language. That means that they have specific semantics that are perhaps a little different than you would think of in terms of a programming language. When you see a statement in constraints, all the expressions in a constraint are evaluated in parallel. They're not evaluated sequentially like you would think of as in a program. There are some special statements that you don't see in regular programming languages, and that's kind of what makes this a domain-specific language. The semantics, the constructs are very specific to the domain that you're working in. The fact is, Python is a really nice base language in which to build what I call embedded domain-specific languages. In other words, building those specific languages directly in, inside Python. It has some really nice features. Sort of the key three features are decorators, which allow you to identify some type and maybe insert some special behavior in that type. Operator overloading is also a fun one, which allows you to redefine what things like A plus B mean. You can say, that doesn't mean addition anymore. It means build me a special expression that will later be evaluated by a constraint solver. And then finally, Python has the with statement that allows you to define statement blocks. And we'll see how these get used in PyVSC. So let's look at an example here. Here I have a Python class that is set up to be randomizable. So the first thing that happens here is there's a decorator. And this basically is a hook to let the library take control over the MyS Python class and instrument it to make it randomizable. So in addition to putting some special mechanisms inside the class, it also defines a method called randomize. And this gets automatically inserted in your class. Now, notice that this is inheriting from the regular Python object class. And it could inherit from any class. And this is part of the reason that the library is very flexible in working together with any other library you might be using. There's no specification that you need to inherit from a specific base class in order for the class itself to be randomizable. Okay, so the second part is we have specific data types that are set up to be randomizable and to participate in constraints. So in this case, we have two lists. In one case, it's a list of 8-bit items, 4 deep. In the other case, it's a list of enumerated values, also 4 deep. And likewise for constraints, we have a decorator that marks this method, AB under C, as being a constraint. So when this class is evaluated, this method gets run once up front to build a set of constraint expressions. It doesn't get evaluated like a method. And you'll see that we have some kind of funny looking, but not terribly ugly statements inside that describe a couple of a for loop as well as then an if-else statement. Now, if-else are special Python keywords, and so we had to get a little creative with the names here to actually be able to take control over these. But all in all, it's fairly readable, fairly straightforward. And again, just to kind of back up my claim that this isn't so different from SystemVerilog. Here we see exactly the same thing written in SystemVerilog. It's about the same length. There's no decorator, but SystemVerilog, there's a class. We have data types declared. The constraints actually look fairly similar, and at the end of the day, oops, you have a randomized call at the end there on your class to actually produce some random data. And the same is true with modeling functional coverage. Here I'll just show these together. Again, on the PyVSC side, to declare a cover group, you annotate a specific class with a cover group decorator. In order to pass data or specify what data can be passed to the sample function, you need to specify the signature. In SystemVerilog, there are special keywords for doing that. In PyVSC, there's a special method for defining the signature of the sample method. Likewise, there are ways to set up, specify what your cover points are, what bins are within there. One actual advantage of PyVSC is you can programmatically calculate your bin structure. You can use a function to divide up an interval and calculate what the key values are. Whereas, of course, in SystemVerilog, you have to type that by hand. But again, more or less the same number of lines of code, pretty close, not terribly ugly. And you could argue with a little bit of training, you could do the translation from SystemVerilog to PyVSC. It's pretty straightforward. Okay, so one note on passing coverage data. PyVSC has a couple of ways to do that. The first way is the one we just looked at, which is you specify what the signature of the sample method is. So in this case, we say that the sample method takes a single parameter. It's a 4-bit integer, unsigned, and its name is A. And via some special Python magic, we cause a class variable to be created with that same name. So this allows you to refer to what the value will be passed via the sample method. And then when the sample method's called, that field is actually, that value is sampled by the cover point that you specified. Now, there's kind of a more general mechanism, which is Python, if you've worked with it, has this notion of a callable. A callable can be a function, a lambda expression, basically anything that you can invoke, and as a function, it can return a value. So we can set up our cover group to accept callables and actually define our coverage goals in terms of those callables. So in this case, our A parameter to the cover group is a callable. And so when we call sample, the cover group or the library will invoke the callable to get the proper value and then evaluate the coverage on top of it. This can actually be really helpful if you're if you have some special logic for example, fetching the proper value and massaging it before you return it back to coverage. All right, so we've captured constraints. We've looked at some random, generation of random data. We've captured coverage, but we want to actually do something with that coverage data. We want to save it to a file. We want to look at it. We want to merge it together with data from other runs. Make some reports, do other fun stuff with it. So how do we do this? Now, this brings us to the connections that PyVSC has to other parts of the Python ecosystem. So I really liked the talk by Alex yesterday on making use of SystemRDL. There are actually quite a few standards out there in the industry that you could argue might get a little less love than they ought to, but are actually represent the work of a lot of people over a lot of time. And one of those actually, in my opinion, is the Unified Coverage Interoperability Standard. This is another Accelera standard. And this is kind of the way that I've chosen to get data out of, coverage data out of PyVSC. So what is UCIS? Well, Accelera is a standards body, and they got a bunch of people together to define a coverage model. Once upon a time. This was a while ago, but not that long ago. So their standard defined 3 things. It defined a coverage data model, sort of kind of how do you think about coverage data? What should be there? What should be tracked? How is it related? How is coverage related to a test, for example? How are tests related to regressions? It's a fair amount of work in terms of defining kind of your thought model about coverage and regression data. They defined a C API that sort of defines how you get data into and out of that conceptual model of coverage. They even defined an XML schema for sort of flattening some of that data out and interchanging it with other tools. Unfortunately, you could argue they didn't provide 2 things. An actual database schema, that would have been great, or a reference implementation. That would have also been great. So if you're familiar with SystemC or UVM, some of these other standards that have a reference implementation you can grab off the shelf, and those are really handy. This doesn't come with one of those. But a lot of the other work has already been done. People have thought through a very sensible scheme for arranging all of the coverage data, how you think about it, and some ways of accessing it. So that is what we're using with PyVSC to get data out of the system and to enable it to be interchanged with other tool flows. The good news is I wouldn't say it's completely widespread, but quite a few commercial tool flows do provide paths to get UCIS data in and out. So I've proven on a couple of commercial tool flows that this actually is a good path for getting data from PyVSC into your standard, coverage viewing tool, let's say, for one of the big three EDA. Okay, so that's kind of this is the companion library to PyVSC, PyUCIS. So this provides a Python object-oriented API to that UCIS data model that is defined in the standard. It also provides a way to read and write the XML interchange format. If your vendor happens to provide, let's say, a shared library with a C API to access UCIS data, it provides an interface to that via the Python CTypes module. And it's set up to support other backends. So if somebody wanted to define, let's say, an SQL schema, and define that, and you could use that via the UCIS API. It also provides some commands on top, for example, to merge coverage data together, to report it out to various textual formats, as well as to do some conversion between formats. So what happens is, we capture our coverage data during our simulation run, write it out using the UCIS API, then we can report it, merge it, view it. There's also a Qt5, extremely simple, but very simple coverage viewer that uses UCIS API to get the data and then display it in kind of a browsable manner. All right, so those are kind of the key capabilities of PyVSC and its companion PyUCIS for working with the coverage data. What it's being used for today, it's actually used in several sort of interesting areas. One is kind of what you would expect for randomization and coverage collection in a Python-based testbench environment. Okay, pretty straightforward. Pretty early on, it was used by the RISC-V project as a way to get a pure Python way of generating instruction streams. And so you can look at how they're using it inside that library. It's been used in a couple of cases for more custom test generation. So for example, in this case, this was actually just presented at DVCon a few weeks ago. The application was to generate firmware with configuration tests to be run in a system. And so they needed constraint randomization. This was a great library to kind of do that. And then on top, they built the actual firmware generation on top of that. And then sort of an uncredited, I know there are cases where this is being used for traffic generation in fairly large-scale multiprocessor systems as well. So you can use it sort of off the shelf. You can use it embedded in other applications. That's one really nice thing about Python, frankly, that you have that flexibility to remix and reuse quite easily. All right, so that's kind of where we are. Where are we going? The first thing I would really kind of point out is the project as it is stable, it's maintained, we fix bugs, people are using it right now. So just because I have kind of a roadmap here, don't think that we have to get to the roadmap before it's of any use. And I'm really very consciously thinking about how some of these enhancements can be brought in with no change to the API, to the user experience. It's really important to have a stability here, and that's a very conscious thing. So one thing that I do see coming, data classes for Python, if you're familiar with them, they're a great way to sort of make your classes a little more concise. And it's one thing that's sort of taken off in popularity since I created the project originally. the next iteration, the next major iteration of the project will be primarily based on data classes. And that gets sort of some user interface improvements as well as improving performance in debug cases. There are some costs that are sort of hidden there when you can't assume that a class is a class is a class of a given type. Python's dynamic nature sort of cuts both ways. I am looking towards more modularity here. PyVSC right now is pretty monolithic. The front-end domain-specific language aspect and the back-end, the randomization core and coverage, it's all one library. And to get more reuse or to enable more modularity and reuse, I'm looking to split that up a little bit. And that really sort of ties into the last point, which is making the randomization and coverage core based on a native language. I'm a C++ guy, so that's what it's going to be. But nonetheless, that will bring performance improvements as well as giving access to a wider set of solvers, which will improve performance as well as, kind of the last point, give access to a wider variety of languages, being able to make use of the core randomization and coverage collection facilities. So that's PyVSC. It's a library for modeling coverage and constraints in a SystemVerilog look and feel manner, with some companion tools for dealing with the coverage data collected. It works with UCIS compliant data, and so you have access to get that into the other commercial tool flows if that's an option for you. Just some resources here, documentation, GitHub links. The last link is my kind of technical blog. So if you're looking for announcements on this or other technology, watch that. So yeah, use it, check it out. And with that, I'm happy to take questions.
Hi, a fan of your work for a long time. I remember following your GitHub account and seeing repos just appear out of thin air for I think a very short period. I do wonder, do you have any comments regarding the performance implications of using Python as the host language?
Yeah, two aspects to that. Python as the host language, as the modeling layer, is actually fairly, the performance impact isn't too bad on that. One place where that does come into play, I mentioned with data classes. With Python and sort of dynamic changing classes, you can't assume that a class with the same name is the same class, every instance of it. You have to assume that the constructor has done something funny and maybe inserted fields and done fun things. So that is one performance impact of the using Python for the front end. That's something I'm hoping to fix with data classes. On the back end, there's definitely a noticeable performance impact, and that's part of the reason, the major reason that I'm moving to C++ as the randomization backend. It's relatively fast right now. I wouldn't say it's competitive with commercial simulators, and no, I cannot tell you any benchmark data.
Thank you.
But yes, it's certainly usable.
So also a big fan of your work, and I can recommend your blog to everyone who hasn't read it. I saw the UCIS viewer GUI, and you had some what looks like a RISC-V core.
Right.
Is that like a public example? It would be great to have something.
Yes, actually, that is. I just grabbed a screenshot from this. Actually, this is data generated from the RISC-V DV generator. So this was kind of the coverage data collected from generating a set of test programs.
Are there any open source projects where you can see these getting used in anger, just as like an example of someone using it?
You know, right now I think I would say that's the biggest thing lacking right now. I'm aware of more people using it commercially than in open source.
Thanks.
But yes, if you become aware, if anyone becomes aware, frankly, I'm happy to put references up to use, because you're right. Having references is really a critical thing, or examples that people can look at and see, okay, here's how so-and-so used it. It's really great. So.
Hi, thanks for your work. It's really great. I had a question about the uniformity of the data that you generate.
Yes.
So how do you guarantee the uniformity, and how does it compare with commercial tools?
Randomness and random distribution it's somewhat subjective. Because we as humans can only look at so much data. You know, you can do a plot, 2 variables, 3 variables, and sort of get a good sense of whether it's randomly distributed. But we're often dealing with 10s, 20s, of variables. And it's a good question. Which ones did you pick? And when you plotted them, are you getting a representative answer? The short answer is it's an area that is continuously being improved. In terms of distribution, I'd say we're pretty good. The latest data that I'm seeing, we're reasonably well distributed. Again, depending on the variables you pick and the constraints, and so on and so forth. It's certainly an area that's you're kind of always investing in, along with performance.
Yeah, and to follow up on that, are you planning to do any type of coverage guided alteration of the SMT sampling?
Yes.
Okay.
No,
yeah.
that's a personal area of interest, so yes.
Yeah, this is great. Very happy for your work.
Good.
Thanks.
Thank you.
Hey, right over here. Really cool work. I'm really excited to check this out when I get home. One question I have is, can you comment on the feature parity against SystemVerilog constraints and what PyVSC can or cannot do?
Yes. Actually, that's okay. I won't pull it up. If you look at the docs,
Okay.
there actually is a table that's maintained that that addresses exactly that. Wrong one, but yes. Yeah, look at the docs. There's a table in there with a feature comparison on both coverage and constraints in terms of what's supported.
Cool. Thank you.
Yeah.
I have a question regarding, so if you move to the backend to using some various more solvers, so that increases your dependency, right? So
Yes.
is it something that, is it worth doing like a fallback that a system without those dependencies can still use the Python approach that you currently have?
Sure. Yeah, yeah, different systems, different solvers. There's a matrix there. I'm looking right now at packing most of the dependencies. Fortunately, most of the solvers are under permissive licenses, not GPL. And so to the extent that can be packed along with the bundle, that will be done. The biggest reason actually for getting multiple solvers is different problems lend themselves to different solvers differently. Throwing a very simple A less than B at a high-end SMT solver is actually going to result in fairly slow performance. Whereas if you threw it at a linear solver, you get an answer very quickly. So that's the primary reason for multiple solvers, more so than sort of speculatively trying out. But
awesome. Let's thank the speaker again.
all right, thank you.
So